So now let's talk about the independent samples t-test, right? And this is kind of our most basic t-test and what William Gossett was kind of originally talking about. But first, let's review a little bit and talk about z-tests, right? And so these z-tests are about things being different from a population. In order to do a z-test, we have to have some information about the population. We need to know the population mean and the population standard deviation on our particular variable. We can create then a z statistic for comparing a single variable to the population, right? Is our single person, our single case, the value for that different from the population mean, right? And that's just the difference between those divided by the expected difference, right? The standard deviation, right? If the difference is bigger than the standard deviation, statistically significantly bigger, then I would not typically expect to see that big of a difference if it's from the same population, right? And this goes to our normal distribution. I'd say if something is greater than, using the two-tailed test, greater than 1.96 standard deviations away from the mean, I would say, well, there's only a 5% chance that I get that big of a difference. Then I say it's from a different, this particular case is from a different population. So that's the z-test for a single variable value compared to the population mean. There's also a z statistic for comparing the sample mean to the population mean. Here, as you might expect, it's the difference between the sample mean and the population mean, right? So this is direct translation here from the individual value, where it's the individual value minus the population mean. Here it's the sample value or the sample mean from the population mean. However, here, instead of saying our expected error is just the standard deviation, here is what we call the standard error, or which is the standard deviation of the population divided by the square root of n, which is our sample size. There are reasons for this, and it has to do with what we're actually testing. We're not so much testing the population itself, but the distribution of sample means within that population. So what we know is that if we take a gazillion samples from the population, and we take the mean of each of those samples, then that mean is normally distributed, has its very own, those means have their very own distribution. It is a normal distribution due to the central limit theorem, and the standard deviation of the distribution of the means is this standard error, which is the standard deviation of the population divided by the square root of the sample size. That's pretty technical, and certainly it's interesting to know, but what's really important here is that our z statistic for the sample mean, comparing a sample mean to a population mean, is not just divide by the standard deviation of the population, is divide by the standard error, which is the standard deviation of the population over the square root of n, which is our sample size. So now if we're looking at, that was the comparing a sample to the population. There is also a z-test for the difference between two means. So we can substitute in the difference between means for that mean, right? So there's a direct translation from here where we have, if we look at the numerator, the sample mean minus the population mean. Here, it's the difference between the two sample means minus the difference between the two population means. And here it was divided by the standard error of the population, which is the standard error, which is the standard distribution of the means. Here, it's the standard error of the difference between means, or the standard deviation of the difference between means. That's our standard error. Again, a little technical there, but there is a nuanced difference. We're really getting back to the idea is the difference between these means a lot bigger than the difference between the population means? And when we say a lot bigger, what we're saying is it different from what we would expect, that standard error difference? And that's what this formula tells us. Now, before we get too wrapped around this formula, here's the thing. This formula requires us to know the means and standard deviations of our two populations of interest. And I have to say, if we have all of that information, like, dude, why are we bothering? Like, we almost don't need to take samples because we have all the information we need from the population itself. And we typically do not have all this, right? We take samples. We don't test the entire population. We just take samples. And so we don't always have, in fact, we typically do not have the population means and the population standard deviations. So what can we do? we use the t-test, right? Our old friend student, William Gossett, created the t-test to look at what do we do when we don't have all of this population information. We can just look at the difference between the means. And in particular, what really was brilliant about what Gossett did when he came up with students t was he came up with a formula for estimating the standard error based on the t distribution rather than basing it on the z distribution, right? And so we have these different distributions and we can use this standard error in order to get there. Now, again, before you get too wrapped around this, I got one more step here, because it turns out that our null hypothesis is that the difference between the population means is 0. So we can actually zero that out to get to here. This is students t, the t-test formula for the t, our test statistic for the difference between two sample means. And what we infer from this is, are those sample means statistically significantly different from one another? And the way we do that is that same way. That numerator is how big is the difference, and the denominator is how much of a difference would we expect. It's the standard error on the bottom here. Now, we use, if you look at that bottom equation, we use what's called the pooled standard error, right? And this is the square root of the variance of sample 1 divided by the sample size of sample 1, plus the variance of sample 2 divided by the sample size of sample 2, and square root of the whole thing. Now, a variance, if you remember, is just the square of the standard deviation. That's why you see the s squared. S is the standard deviation, s squared is the variance, the squared standard deviation. That's our pooled standard error. That helps deal with the fact that oftentimes our samples are different sizes, that each sample will have different standard deviations. We use that pooled standard error at the bottom. Now, the other thing is don't forget that t is based on a degrees of freedom. We have a different t distribution based on the degrees of freedom. The degrees of freedom for this independent samples t-test is the sum of our samples, so our grand sample, the sum of both the sample from both groups minus 2 gives us our sample standard deviation, or excuse me, our sample degrees of freedom for our t-test.